Okay, this is sort of our example, our answer maybe to Google's self-driving car. This was a project done some years ago by a couple of students that wanted to build a car that would drive itself. And so they mounted a webcam on top of, this is the frame from a radio-controlled car, but we've ditched all of the radio control elements so that this is supposed to be an autonomous car. Now in this case they're not using an Arduino, that's a Raspberry Pi on the front. You may have heard of that. That's a complete computer in its own right. And then it connects to the motor and it can drive the car, and it also has a way of steering so it can make the car go wherever it needs to go. But a webcam up here is connected to that. And the idea was for this to look and see the path ahead and decide how to turn left or right. And the interesting thing is that the students had this all working before the show. The trouble was they programmed it in a language, they used Python. And Python is a good language for many things, but it is not a very fast language. For many applications it tends to be somewhat slow. And in this case they needed to be doing video analysis. They needed to be looking at the view ahead and analyzing that scene and doing that pixel by pixel to try to figure out where is the road. Is it curving to the right or to the left? And doing all of that analysis in Python was very, very slow. And so they had the car working in every respect. But it had to be programmed to run at a snail's pace in order for it to be able to do the analysis of what was coming up and to turn appropriately and to stay on the road. And so they had it working, but it was just crawling along. If they had it going any faster than that, it would lose track of the road. So that wasn't very impressive. This was the night before the show. Everything was working, but it was too slow. Well, one of the students in that group was a computer science student, and a very capable one. And he decided to pull an all-nighter. And he took all of the coding for that was in Python and rewrote it in C. And he did that in one night, and he had it working the next day for the show. And on the day for the show, this car was racing around the floor. They had gotten it working so well that it could go fast enough that they ultimately had to put a tail on the back end of it with a little kill switch, essentially. You'd stomp on the tail and it would pull the wires out and stop the car, because it would get away from them at times and go streaking towards the wall, and they had some way of stopping it. So they had to do that. But this thing was racing around. It didn't work perfectly. Now and then it would lose the road, and then they programmed it to just go around in a big circle until it found it again, and then it would chase off again. It was great fun. So I was just really pleased with how well that one turned out. So here's another project that came from the show just this last year. Students were taking, this was a little scooter that we bought at Walmart and took off the handlebars and such. But it's a powered scooter, so it will make itself go. And the idea was to try to make it also balance itself so it would stay upright. And so students worked on this a lot, and you can see a video of this. It's part of the show. And so I would encourage you to watch that video. It shows all of the different projects, but this was one of them that students actually got working in a really good way. For the first time, it goes all the way down the hallway and stays balanced the whole way. So yeah, so take a look at that video. You'll see lots of other projects too that you would be interested in doing. This is a class you will take. If you come to Goshen College and you're a physics major or an engineering physics major, you will take this course, you will do a project like this, and you will enjoy it. So what I want to show you here is an experiment that you folks will do. Maybe I'll turn this off for just a moment. It's rather annoying to me, but this is an experiment you will do your very first semester here. So as part of our sort of introductory engineering and physics course, you'll do a bunch of things, and this is one of them. This is an experiment in which we're looking at the resonance modes or vibration modes of a plate, a piece of aluminum. And so students just cut a piece of aluminum in some interesting shape, and then they study the resonance modes of something like this. And even any old object like this will have a bunch of different modes, different vibration modes, and we can study these using this electronic laser holography system. So there's a laser shining on the plate. This is the plate that we're looking at right here. And then at the same time as looking at that with the camera and special optics that transform that into an image, we're also blasting sound directly at the plate. And what we'll find is that if we hit just the right frequency, it will vibrate, and that shows up in the holography image that we're seeing here. So let me turn the sound back on. Now you don't see much yet. That's because the frequency isn't quite right. It's a very specific frequency we have to find, and I'll just tune it up a little bit. And there you can see the vibration pattern coming in. These are places in the plate that are moving a lot, vibrating back and forth. The white places are nodal lines, and that's places where it's rocking back and forth and not moving very much. And so you can see the whole vibration pattern right there, and here we can see the exact frequency at which it vibrates. And we can compare this to a computer model, because you will also, in this class, put this very same plate, you'll make a model on the computer that will predict this very same pattern. That's the kind of experiment that you can do here at Goshen College as an engineering physics or a physics major. Okay, so here we have an interferometry setup. This is the laser we're using at the moment. It's a helium neon laser, but it's running in a green, at a green wavelength. So that's the beam that's coming out here. And then it goes through a special kind of filter that effectively spreads the beam out. And I think you can even see that a bit here. That's how the beam is spread out nicely. And we can even adjust the size of it if we want to, but we'll leave it about like that. And then it goes into the actual interferometer. This is a Mach-Zehnder interferometer. This is a beam splitter. Some of the beam goes through, some of it reflects down this direction, and then on this direction. And the other part of the beam goes through that one, comes through here, and then they both come together for the direct path, and they could interfere here. So take a look down here, and let's see if you can see the interference pattern. We look for a series of bars here, and we don't see one. All you see is a big blob there. There's no interference pattern. But if I change things, because right now I've got a couple of polarizing filters, and they're set the wrong way. They're set so that one beam is polarized and the other beam is polarized 90 degrees to it. And when they come together, they don't interfere. But if I change the polarization direction of the two beams, now you see the lines of an interference pattern. Let's see if I can get this set. There is a nice strong interference pattern. You can see the bars of the interference pattern, and that's because the two are now in the same polarization direction. So when they interfere, you get an interference pattern. When light from two, if you split light into two directions and bring it back together again, they have to be of the same polarization or you don't get interference. That's one simple thing that you can demonstrate with this. There are many, many more things, and if you want to do this, you need to be a physics major at Goshen College.